I want to talk about the chi-square test, and today we're going to look at um, the test of independence. Remember that chi-square has two different tests, or it has multiple tests. There's actually three of them in this book that they talk about: the goodness of fit test, the test of independence, and the test of homogeneity. And the chi-square is a pretty good test. It's useful and has been around for a while, and it's pretty popular. So, uh, what is it used for? That's the first question. And when we talked about chi-square, we said that it will try to compare qualitative data. And in this test of independence, we're going to look at comparing two different qualitative variables. So it sounds a little like correlation. Correlation was kind of our first introduction to comparing more than one variable. We had more than one sample before, but we had like one sample means t-test and two sample means, but they were testing the same thing. Um, and with chi-square or with correlation, we said we would actually look at two different variables. And so with chi-square, we also are testing two different variables. But the difference is, again, correlation uses quantitative variables and chi-square uses qualitative variables. So here they start out talking about contingency tables, and we kind of organize our data in contingency tables. There are tables, rows and columns that list counts. So we need to always go out and collect some data, and then we need to organize that data. So when we have a couple qualitative variables, we create this. It says contingency table or two-way frequency table. And remember, we had frequency tables when we had a sample of data and we wanted to organize that data. That was a very popular way, frequency tables. Now this is again, two-way, meaning we have some rows and columns. So it's a table consisting of counts of categorical data corresponding to rows and columns. The row variable, and we have a column variable. And the test of independence, we test the null hypothesis that in the contingency table, the row and column variables are independent of each other. Okay, so let's look down here. We have this test statistic, this formula to calculate the test statistic. And this is the same one used with the goodness of fit test and the test of homogeneity. We're taking chi-squares, the sum of the observed minus expected squared, all divided by the expected. And we actually work that out by hand with the goodness of fit test, because all of the TI-84s won't do, they don't all do the goodness of fit test. So the newer ones, it's kind of getting to the point where eventually all the ones that are out there will be able to. But we worked it out by hand, and then we were looking at then the results of those comparisons of the observed and the expected values for all of the different parts of the column variable. Now, here they're giving us a formula for expected values, and the difference between the goodness of fit test and the test of independence is that the goodness of fit, we said, had predetermined expected values, so we didn't need to do this. The test of independence did not have expected values given. So we can find them by using this formula here. All right, so let's move on here. And they say the critical values are found in the table based off of degrees of freedom. And when we looked at the t-test, we had to do basically the same. But in the t-test, degrees of freedom was just n-1 per sample. And in this case, though, the degrees of freedom for chi-square is a little bit different. It's saying here that you take the row, number of rows in the table, -1, times the number of columns in the table, -1, and you multiply these two things together. So we're going to do an example of that. And number 2 here, tests of independence, when we do the hypothesis testing, are going to be right tail tests. So that kind of cuts down a little bit of confusion setting up those hypothesis tests. So let's look at this example here. Finding expected frequencies first, and then we're going to do the chi-square goodness of fit test, test of independence on this information here. So what they did is they collected some data from different treatments for stress fractures in a foot bone. And we see we have 4 different types of treatment: surgery, weight-bearing cast, non-weight-bearing cast for 6 weeks, non-weight-bearing cast for less than 6 weeks. And we have 2 columns, success and failure. Now the 54, 41, 70, 17, 12, 51, 3, those are the observed values. 54 people that had surgery, well, it was considered a successful treatment. 12, not successful treatment, right? Weight-bearing cast, 41 successful treatment, 51 failure treatment. So wow, looks like there's a big difference there. 70 successes, cast for 6 weeks, only 3 failures. Not so bad, that's pretty good. Non-weight-bearing cast, less than 6 weeks, 17 and 5. Okay, so there's our data. Now the E had to have been calculated. So these are all different because we have different sample sizes for surgery. Look, we had 66 surgery. We had weight-bearing cast. We had 92 in that column or row. 73 here, 22. So to figure out what the expected would be, we got to go through this formula and figure out what that would be, given that the row and column variables would act independent of each other, or that there would be no difference between the observed and expected values as we look through this. So the null hypothesis, in a sense, is saying that this number here and this number here would be equal. This number here and this number here would be equal. This one and this one, this one. Okay, so no differences. Now let's see, how are they getting these numbers in the parentheses? Well, we're supposed to take the row total. So this 54 is in this row. The row total is 54 plus 12, or 66. Column total that 54 is in, it's in this column. I add up 54, 41, 70, 17, and I get 182. Row total, column total, total, right? All of them. So we got to take 54, 41, 70, 17, 12, 51, 3, and 5. Add those all up, and you get 253. Then 66 times 182 divided by 253 is 47.478. So that's where they got this number at here. Because we use the row total for 54 and the column total for 54, that's why we put this here with 54. Now let's do this next one. 41 and 51. So this is my row total. 92 would go right here. 92 would go here. This same column, so these numbers add up to the same number right here. The total always stays the same for all of these. It's 253. So for this, the only thing that changes is this number right here. 66 now becomes 92, right? We got 66 from here. Here's 92. We put 92 times 182 over 253, and we get 66.182. If we take 70 plus 3, 73 times 182 over 253, we get 52.541. And then if we take, this is 17 and 5, So we take 22 times 182 over 253, we get 15.82. And so it's pretty straightforward. You run through a few of these, you'll catch on to that. All right, so you got the expected values. Now we're ready then to do the hypothesis test. All right, so again, success is independent of treatment, alternative or success that are dependent of each other, right? So there's our null hypothesis. It's a right tail test. And we need a critical value. So the critical value we could work out by hand, like we did with the goodness of fit test. Let's go back. I just want to show you what I mean by that. You would have to take the observed minus the expected. So 54 minus 47.478 squared, all divided by 47.478, plus 12 minus 18.522 squared, all divided by 18.522, plus 41 minus 66.182 squared, all divided by 66.1. And so you do that observed minus the expected squared all over the expected, which was the formula. The chi-square test statistic formula, which is right here, right? Test of independence. And we did that with the goodness of fit test. So same. All right. Now, so we're not going to do that though. We're going to use a calculator. I'm going to show you how to use the T84 to get all this. So it'll save us some time. All right. We need to put the data in first. So let's go back to the table. The data goes into a matrix, or a matrix is just a table of numbers, rows, and columns. Also like this. So let's go into matrix. So second function, matrix. And then we go over to edit. Hit enter. And we plug the numbers in. I already did that. So 54, 41, 70, 17. Now you got to make sure you type in, if it's not a 4x2, this has 4 rows, 2 columns. If you were playing with something else in your calculator and this comes up something else, you got to get in there and type in 4x2. 4 rows, 2 columns. And then put your data in exactly as it appears here. These are observed values exactly. 54, 41, 70, 17, 12, 51, 35. Okay, so we got the data in. What do we do with the expected numbers? Nothing right now. Okay, nothing. Put the observed in, go to stat, test, chi-square test. Not goodness of fit, chi-square test of independence. Enter. Go down to calculate. We're not going to do anything there, just hit calculate. And there's our values. So you notice they did this all by hand. And they got 58.393. We'd use the calculator, we got 58.393. So you're going to come up the same either way. Now, they gave you the p-value too here. 1.29 e to the negative 12. So that's a point. See right here it says they used this Excel stat and they got less than, they're saying the p-value is less than 0.0000. So it means it's way out there. So it's definitely reject. Once you get out there so far, they just, in the programs all the time, they cut it off and say, hey, it's less than 0001, so we don't need any other zeros. Because this is like, do we need to write out 11 zeros, 1296? No. But you could just write it like this, 1.29 or 1.296 e to the negative 12. And that would be good enough. Degrees of freedom, how did they get that? Let's go back to that. Degrees of freedom. Well, this table is a 4 by 2. Row minus 1 times column minus 1. So that means not 4 rows, but 3 times 1, or 3. So you subtract one of the rows and one of the columns, and you're left with 1, 2, 3. If I take this row out, row minus 1, take this row out, take this whole column out, I'm left with 1, 2, 3 numbers, 3 cells, right? That's what that's standing for right there. Okay, so we got our test statistic, critical value. They don't give us that here. We could get it off the table. We could look it up on our calculator. Remember that we have these distributions, so we could go second distribution, and you'll see chi-square CDF. Enter. The lower value, well, it doesn't seem lower, but that's an awful big number, 58.393. Upper value, E99. And E99, degrees of freedom, 3, paste. So what we're doing is trying to find the area under the chi-square curve from 58.393 to infinity. And you'll see 1.29 e to the negative 12. So you get the same thing, right? So let's take a look at this. And see if we can keep these up here. So we have a chi-square, and well, it's not going to let me have them all up at once, so let's just erase that. Oops. I have to use my pen to get that out of it. All right, let's go over here and kind of wrap this thing up. So this is my chi-square, and this is a test of independence, right? Chi-square test of independence. So I'm just going to draw the graph. Roughly looks normal. Okay. But starts at 0 because all of our values we square. We take observed minus the expected squared makes it positive. We're never going to have a negative number, so we don't need anything down there. We're going to be here, and right here is going to be 1. So that's going to be most likely to occur. And remember that the chi-square test of independence is a right-tailed test. Right. Now, if we look up our critical value, so we'll see here the critical value, that's the table value, 7.8147. Now, our test statistic, right? And again, it's way up there, right? Which was 58.39. We'll just do 39. 58.39. And then, so, right, our p-value is the area beyond this. So this we don't need right now. Let's take this off here. That area is going to be, well, we can put it up there. Let's say we set our significance level at 5%, 0.05, right? So this is 5%. We're running a significance level of 5%. So remember the significance level. So that's at alpha equal to 0.05. So what is this number here, right? That's the predetermined probability of a type 1 error, right? So this is predetermined. We set this up so it means that we don't want to have more than a 5% chance of wrongfully rejecting the null hypothesis. All right. Well, what's the p-value you have to deal with, right? Now, this also is the probability of a type 1 error, right? P-value. And our p-value was 1.29 e to the negative 12. So that thing was a bunch of zeros, right? So there's not much area. We're saying there's tiny, tiny bit of area really beyond 58.39 under this chi-square continuous distribution. This is like the normal distribution. It's continuous, all right? And we use it to find probabilities. So these numbers are probabilities. This 1.29, right, e to the negative 12. So we're saying that the difference that did occur was very unlikely to have occurred by chance. So we're claiming that there is a dependence between the row and column variables, right? So we're going to, since P is less than alpha, we're going to reject H sub 0, row column variables are independent of each other, okay? Row and column variables of independence are null hypothesis. We're rejecting that the row and column variables are independent. We're saying that they are dependent. So in other words, let me pull up the, so let's take a look at this. Remember what we were doing. We're checking to see, are these all the same? We're basically the same success rate for surgery, weight-bearing cast, non-weight-bearing, non-weight-bearing cast less than 6 weeks, right? Success and failure, right? Nothing to do with type of. That was our null hypothesis. We're rejecting that. We're saying that, yeah, it does. In terms of success, it really does make a big difference, whether you have surgery or cast or non-weight-bearing and so on. So does that help us? What can we do with that? Well, again, obviously would help us kind of check to see the type of treatment that we might want, right? If we have any broken bones in the foot. And another thing that he talks about here is he says, let's say that we wanted to look at, here's a rationale for expected frequencies. To better understand expected frequencies, pretend that we know only the row and column totals in table 11.6. Let's assume that the row and column variables are independent and that one of the 253 study subjects randomly selected. Okay, so we're going to randomly select one of those people that had something done to fix their broken foot, right? So the probability of someone, right, getting counted in the first cell, right? Remember, there were 253 people, right? We randomly select one. Surgery, well, there were 66 people that had surgery, right? And 182 out of the 253 total successes. That's what everything. So it says if the row and columns are independent, as we're assuming, we can use the multiplication rule for independent events. So just remember, this is a test of independence. So how does that help us? Well, remember for independent events, we just multiply. We use that multiplication rule. The denominator stays the same. Sample size doesn't, or our sample space doesn't change as we go from one trial to the next. So like flipping a coin, 1/2 times 1/2, right? The coin stays the same because the tosses they're considered independent of each other because the options when you flip a coin don't change as you keep flipping it, and we're saying the same here. So if they were independent and we knew that, we could just multiply that thing out like that. This times this, you get 18, right? Now, with the probability point for the first cell, we expect that among 253 subjects, there are 253 times 0.187, which is 47.78 subjects, right? So let's see what we had. 47. So 18%, 47.4. And that's what he's trying to show here. There's our, again, we're saying that they're independent. That's what these numbers are all saying. Okay. And the last thing here, we're not going to do any, the test is exactly the same. It's just a theory. The chi-square test of homogeneity is a test that claims that the different populations have the same proportions of some characteristic. So you start out by saying that the populations are different, and you test the thing. And here's an example. They had a wallet. Whether a lost wallet is returned is independent of the city which it was lost. Lost wallet being returned depends on the city. Okay. And then they go through, they use StatCrunch, which is another, that's a freebie program that you have you can use with the Trello book. So they just went here real quick and did the chi-square degrees of freedom, 15. So they must have had 16 cities involved, right? Here's your chi-square, your test statistic, and your p-value. And they're saying we reject independence. So there is sufficient evidence to conclude that getting your wallet returned would be different depending on the city that you're in. Okay, so populations would react differently. Now here's the table here. Wallet returned, wallet not returned. And here's all our different cities in here that they were using for that test. And that's really about it for the there's exact test. We had an assumption with chi-square that our expected values, if they got too small, kind of messed the test up. And we were a little concerned, and it said that every cell must have an expected frequency of at least 5, and this requirement is necessary for it to be a suitable approximation to chi-square. And it says Fisher's exact test often used for 2x2 contingency table with one or more expected frequencies that are below 5. Because the exact test does give you an exact p-value, does not require an approximation technique. So but you don't have to know. We're going to skip that, and we're just going to conclude there and get ready for the last exam.